Okay, so now we're going to start looking at some practice problems in the classical mechanics book. Or I'm sorry, not the classical mechanics book, the Intro to Modern Physics book by Kenneth Krane. So this is the very first one. The first section is a review on classical mechanics. I'm doing like notes on it as well, which I've been posting. You can watch the series on modern physics. And we talked a lot about things like Galilean relativity and what have you, but we're also going to review some of the other concepts of classical mechanics because it turns out they're really related to modern physics, just in a slightly different way, including momentum. So let's review a little bit of momentum and energy. Momentum and energy. It says a hydrogen atom of that mass is moving with a velocity of that speed, and it collides elastically with a helium atom of that mass, which is at rest. After the collision, the hydrogen atom is found to be moving with a velocity of that velocity in the direction opposite of motion, hence the negative. The negative right here, that's what that's implying. Find the velocity of the helium atom after the collision in two different ways, by applying the conservation of momentum and by applying the conservation of energy, two very important concepts that's worth reviewing. So let's talk first about part A. Conservation of momentum, that is your momentum that you initially have in a system is equal to the momentum that you end up with in your system. Okay? Well, what momentum do we have initially? We have the mass of the first object, which was the hydrogen atom. We'll call this mass 1, and we'll call this mass 2. It's pretty subjective, but that's what we're going to call those. So mass 1 times velocity 1, initial. So the initial velocity that you have, plus mass 2, V2, initial. So that takes care of this part of the equation. And that's going to be equal to mass 2, V2 final, plus mass 1, V1 final. Okay. Well, we can simplify this because it mentions that what we're calling the helium atom, mass 2, was initially at rest. So if that's the case, it doesn't have any initial velocity, so that goes away. Now, we want to find the velocity of the helium atom, the final velocity. So it's worth noting real quick what we have. We're given mass 1, mass 2, V1 initial, V2 initial, which was 0, and we were given V1 final. And what do we want to know? What's our end goal? V2 final. That's ultimately what we want to figure out. That just helps us be a little organized with these problems because you might forget which one's your helium mass and your hydrogen mass. Just write that down on the side. It's a good practice for any physics problem. Okay, so now that we know that this is what we want to solve for, all we have to do is isolate it because we know everything else. So we have M1 V1 initial minus M1 V1 final, all divided by mass 2 is equal to V2 final. Okay? So all we have to do is plug in. And if you were to plug these numbers in, you'll get V2 final is equal to about 4.53 times 10 to the 6 meters per second. Okay, so that's the final velocity of the helium atom, and we use conservation of momentum to find it. But part B wants us to find the same answer, so this should be an easy check, but using conservation of energy. In other words, energy final equals energy initial, right? Energy is conserved in this particular case. Okay, well, we have to think of what kind of energy we have in our system here. And really, there's not going to be any potential energy. In fact, the only type of energy we're going to be looking at in this particular case is kinetic energy. So what we're really interested in is kinetic energy final equals kinetic energy initial. And it's the same idea, except instead of just mv like we had before, kinetic energy is 1/2 m1 is what we'll start with, v1 final squared, plus 1/2 m2 v2 final squared. These are still vectors. Okay, so that takes care of our final part, plus 1/2 m1 v1 initial squared, plus 1/2 m2 v2 initial squared. Well, it's still true that the initial velocity for the second atom is 0, so that makes it a little nicer. And it's still true we want to know the final speed of the helium atom, so that's just that. Simplifying it a little bit, we can multiply everything by 2 to get these 1/2s to go away. And now it's just algebra. So v2 final squared is equal to m1 v1 initial squared minus m1 v1 final squared, all divided by mass 2. And then if we take the square root of that, we should get our answer here. Cool. So if you were to plug this in, you should get about 4.53 times 10 to the 6 meters per second. So hopefully that makes sense. Just kind of a review on some of our conservation laws, which is always important if you don't remember that from Physics 1. And we'll do more of these. So if you're not familiar with a lot of our concepts in Physics 1 or Physics 2, it's okay because we're going to go over it.